Hello everyone, this is Mohammed Yaqub. I'm back again with another interesting STM32 tutorial. And today's tutorial has been one that people waited for very long for, and that's the STM32F4 Discovery Audio Codec. So that should be a really exciting video. So the STM32F4 Discovery utilizes an audio codec, which is the CS43L22, this chip over here, that can connect to the STM MCU and output audio through this audio jack. Alright, so before we get started, let me just give you a brief idea on how this audio codec is connected on the STM32F4 Discovery. So we're going to look at its schematic, and that should be on you need to open the user manual of the STM32F4 Discovery, go to page 34. Yeah, and that should be the audio schematic. And as you can see over here, to give you a little background on the audio codec, it uses I2C interface to communicate with the MCU for the configuration of the audio codec chip. And it also features an I2S interface for the audio signaling, and it has got an analog input too. So you can stream audio to the audio jack either through an analog output on the STM, so that would be a DAC output, or using the I2S interface. And in today's video, I'm going to show you the two methods. In the first part of the video, I will show you how to use the analog input of the audio codec and how to stream analog data from the STM straight to the audio amplifier on the headphones on your STM Discovery board. And then towards the second part of the video, I'll show you how to use I2S interface to stream audio data in a similar way. So I think that's enough to get us started. So let's open CubeMX and set up a project. And on CubeMX, click on New Project. And we need to select the right board. It's the only one, STM32F4 Discovery, the one with the audio codec on board. So go to Board Selector, Discovery Board, and it's the F4 Discovery Board. Alright, and the first thing we need to do here is I'll clear all the pinouts as usual, and we're going to set the audio codec pins one by one. Let me start by enabling the onboard LEDs. They might come useful. So I'm going to enable all of them, PD 12, 13 and 14, and 15 as well. And then back to the schematic, and we can clearly see one of the most important pins is the audio reset pin. And that's on PD4. So we need to enable a digital output on the STM board to control this pin. So that's on PD4. So you need to enable PD4 and set it to digital output. And then we need to enable the I2C interface to communicate with the chip. And that's on I2C1 apparently, on pin PB6 and PB6 for clock and PB9 for data. So let's do that. I think it's on I2C1, enable it and set it to I2C mode, and say PB6, but I need to map this to PB9 instead. So just go to PB9 and enable the data, and it will automatically swap to PB9. Perfect. Next thing we need to do is that we need to enable I2S3 interface to provide the clocks for the audio codec circuitry. Even though we're going to use analog input in the first mode, but we still need to enable I2S to provide the clock signals, right? So that is I2S3. Let me enable it, I2S3, and we need to set the mode to half duplex master mode. And we need to enable a master clock output. Now let's just verify the pins really quick. So master clock got mapped out to PC7. And that's exactly the one on the schematic, and I2S clock should be on PC10 and is serial data on PC12. Let's just verify that. Perfect, here they are, PC10 and PC12. And now for the word select, this got mapped to PA4 as the correct one. However, we need to use PA4 for this mode for the analog output of the STM as shown on the schematic. So PA4 is also the analog input. So you're going to temporarily just map this to any other pin. Click on control and then left click on the mouse and drag it over to the alternate pin highlighted in blue. So any other pin really, because we don't need the word select pin for this analog mode. And instead on PA4 we can enable a DAC output on the STM. Alright, and that's it. That's all the pins we need on the STM board. So just some final things. I'm going to enable the external oscillator to provide just to use the maximum clock speed. And also one more thing I need to do is that I need to enable a timer to provide the sampling rate for the analog output. So enable timer 2 and select the clock source to internal, and that should enable timer 2. And now let's move into the clock configuration window. We're going to select the external clock oscillator source and set the clock to maximum speed 168 megahertz, and that automatically adjusts all the other clocks. Now to the configuration window. First, I2S interface. I'm going to use the standard I2S, the Philips standard, 16 bits on a 16 bits frame, audio frequency to 48 kilohertz. This is just to provide the clock signals again. And then I will enable a DMA on the I2S line. So select a DMA on the TX, the mode to circular, using a FIFO, threshold full, single burst size, and the data width to half word, which is 16 bits, and increment memory. That's all, and click OK. Next thing, I2C, I think I'll leave that as default, and then the DAC output to also default. I'm not going to change anything. And now the timer. This one should create 48 kilohertz sampling, or let's say 50 kilohertz for my analog output. And go to the parameter setting, and you can see that we need to set a prescaler. I know the timer 2 clock source now is at 84 megahertz, so I'm going to divide it by 84 to get, so 84 mega divided by 84 will get me 1 megahertz, and I want to achieve 50 kilohertz sampling rate, so 20, and it's important to put the -1 as well, and that should, when I divide it by 20, that should get me to 50 kilohertz. Perfect. So that is a 50 kilohertz sampling rate with timer 2, and I'll show you on Keil what I mean and why do I need a timer interrupt at 50 kilohertz sampling. All right, and I need to change the trigger event selection mode to update event and enable the timer interrupt, and that's it. Click OK, and we're ready to go. So we're ready to generate a source code. Click on generate source code icon. I want to select the location to store this project in. I'm going to store it in here, and I'm going to call it Audio Codec Video. Select the right IDE. It's Keil Microvision 5 in this case, and click OK. And while this is loading, for any of my business contacts, you can get in touch with me through my own company's website, mutexembedded.com. All right. And once source code is generated, click on Open Project, and this will take you to your IDE. All right, and first thing we'll do in Keil here is that we're going to compile the project. We're going to compile it first. And while it's compiling, we're going to go to the folder and copy the library files. So what you need to do is that you need to copy the library H and C file for the audio codec that I'm going to include down in the description of the video, provide you with a link to download these library H and C files. So you need to copy them to your project location where you selected to store your project in. Mine is just in here, audio codec video. And navigate to the MDK ARM folder and copy them over to here. Now back to Keil. It's still compiling. We'll just wait for it to finish compiling, and then we're going to carry on the next step. All right, perfect. Done compiling without any errors. Now next step is to add the library C file to our project. So right click on the application user folder and add existing files to the group. And we're going to select the library C file. And now we also need to add the path to the MDK ARM folder for the compiler to see our header file. So click on options for target and navigate to C++, include paths, and add a new path. And click on this and select the MDK ARM folder, and that should include the library header file path to the project. Now navigate to the library C file and copy the header file and put it into our main. Okay, and now we can use the library. So I'm going to go to the library H file And first function we need to use is the CS43 initialize function to initialize the audio codec device. We're going to start using it on bigger number 2 after doing all the initializations. And the first parameter this function takes is the I2C handle to communicate with the audio codec. And the second parameter is the mode, so either we're using the analog mode or I2S mode to stream audio data. And as I said, I'm going to first show you how to use the analog mode. So at this first part, we're using the analog mode. All right. And then the second function we need to call is set volume, perhaps. And the volume is from 0 to 100. So I'm going to call set volume and pass 50 to it. I'm just going to output a medium volume. And then the next function we need to call is the enable right left. So we either want to enable just the right side of the headphone or left side or both of them. I'll just enable both of them. Right? And you can see in the H file a define for it, right left. And now we can call the audio start function to start the audio codec operation. So that should set up the audio codec, but you're not going to hear any audio at the output just yet. Next step is to start the DAC, just to start the DAC operation as well. And you'll find this function into the DAC-C file, digital to analog converter, and there should be a function called HALDAC start. I'm going to call it in here. Alright, and this function takes few parameters. It takes the DAC handle, which is defined by CubeMX and given the name HDAC. It takes a pointer to that, and the second parameter is the DAC channel, so we're using DAC channel 1. And that's it. And then now we need to define the timer interrupt callback that is going to sample at 50 kilohertz sample. And by the way, I haven't explained a lot about this analog method. This analog output method is quite useful if you are streaming audio data sample by sample, and that's why I'm using the timer interrupt that interrupts at 50 kilohertz sampling rate. It's quite useful if you have a processing algorithm that you're doing real-time processing and output to the audio. All right. So back into this, you go to the timer.c file and scroll down towards the bottom. I'm not sure which line it is, but it would be down there. Here we go. And we're looking for the timer period elapsed callback function. And here we go. Here it is. So it's a timer period elapsed callback. You need to copy this, but without the weak object, to our main and bigger number 4 down there. And we're going to put our code. So this should sample at 50 kilohertz once we start the timer. And in here, I'm first going to check if the timer that caused this interrupt is our timer, which is timer 2. I've checked the instance. If the instance is equal to timer 2, which is our timer for the DAC, then we know that we can proceed and output a sample to the audio. Okay. To make this operate, we also need to start the timer interrupt. So we do a similar thing. We started the DAC. We also need to start the timer interrupt. So start TIM2 using a function called HALTIM start time base and start as interrupt. And this just takes the timer handle, which is defined also by CubeMX HTIM2. We need to pass it as a pointer to this, and then we'll start the timer 50 kilohertz sampling rate interrupt. And next, we need to build our sine wave. So I'm going to build a sine wave of, let's say, 1 kilohertz, so that we output this as an audio through the audio codec. So to use the sine functions, we first need to include the math library. So include math.h, and I'm going to use the floating point sine function. So that's sine if, and I'm going to build a sine wave. So I'm going to create a variable for it. This returns a floating point variable. I'll define it globally here. Call it float my sine value. So just a temporary variable to store the sine value. Back to here. So and this will take a to generate a discrete sine wave. We would have to use an indexer and the time period for each index. Let me explain to you briefly how this is done, but I'm not going to get into much details, just to get you comfortable with it. So in a continuous mode, if we have a continuous sine wave, it will look something like this. We have a sine of 2 by f, and then we have t, our time variable, and when you plot it, it looks something like this. It's just a continuous sine wave. Whereas a discrete one, the discrete version of the sine wave, it would the function would be sine, and then I as an index. We still have the 2 by, but now the frequency is governed by the sampling rate, which would be, we multiply this by some sort of delta sample, I'll call it. I'll explain to you how this works in the code. So this will create, let's say, 50 samples per one cycle. And since our sampling frequency is 50 kilohertz, then for 50 samples, the audio output would be at 1 kilohertz, right? If you think this is still confusing, just Google it and see how the discrete sine is implemented. I'm going to write it now in the code. I'm sure you will easily figure that out, right? So that will be an index. I'll call it IT, a time index. Multiply this by 2, multiply it by pi, which I'll need to define at the top. So I'll define a variable for pi, define it at the top here in the private variable section. So 3.14159, and I put an f at the end to mark that this is a floating point variable in the memory. So I'll multiply this by pi, and then we need to multiply it by a magical variable that I'll call sample n. So let me define it at the top. So first we need to specify, I'm going to define variables as well, constant variable to specify the sampling rate and output frequency that we want to see at the output. And I'll define constant variable for those. Let's say define if sample for the sampling frequency, and that's 50 kilohertz. And I know my desired frequency output is 1 kilohertz. So I'll set 1 kilohertz. And then I'll define those variables, the magical one that I mentioned, which I'll call sample n or sample dt for the, and sample n. And they're defined as follows. I need to define them at the main. So sample dt is equal to frequency output divided by the sampling frequency, and you will see why that's the case. And the sample n is the other way around, equal to the sampling frequency divided by the output frequency. Just hold your breath for a moment. I'm sure you will figure this out really quickly why that's the case. And I'll also define a variable for my time indexer, which is that I already written down there. It's IT, the time index. All right, let's go down there into the timer interrupt callback. So I define a variable for this, and now I need to multiply this by the sample dt. And then what I need to do at the end of the loop is that to check if the index, I need to increment the index first, and if the index got above or equal to the sample n, variable I defined at the top, then I'll restart the IT back to 0. Right, let's do the quick math quickly here. So the sample dt, we say it is equal to the frequency out divided by the sampling frequency. So that will be 1 kilohertz divided by 50 kilohertz, we get 0.02. And the IT going to go from 0 to sample n. Sample n is 50 kilohertz divided by 1 kilohertz, is 50 samples. So what's going to happen basically is that this one, 2 by, sine 2 by is just one period. So it's going to go from 0 to 50 and create one sine period. So it will look something like this. So it will create 50 samples. It will take 50 samples to make one sine period. And because my sampling frequency, I set it to 50 kilohertz, then that will ensure that we get 1 kilohertz at the output, because this got divided at 50 samples. Just pause the video here if you think you didn't get it. All right, next we need to convert this sine value, convert from float to decimal in order for us to output it through the digital to analog converter. And for that, I'm going to define a variable, unsigned32 variable, Find an unsigned 32 variable. I'll call it my DAC value. So this is a value to be output to the DAC. And this simply equal to whatever Sine value we get from the Sine function. And we know Sine will output a value from -1 to 1, but because our DAC cannot output a negative value, so we need to add 1 to it to shift the Sine by 1. So to shift the Sine by 1, and that will be from 0, the range will be then from 0 to 2, and I'm going to multiply it by 127. The reason why I multiply it by 127 is because I want to output just a single byte to the DAC, and 1 byte is equal to 2 to the power 8, which is 255. And because I've got the negative and positive divided by 2, I get 127. Right, and then I just need to output this, output the signal or output the sample to the STM DAC. And to do that, we need to call HAL DAC set value. This function takes few parameters, takes the DAC handle type diff, and it takes the DAC channel, which is DAC channel 1, because on PA4, and it takes the data alignment or the data size. So that will be DAC aligned. We're outputting 8-bit right aligned, and I need to pass a value as my DAC value, the decimal value of it. Alright, and that should output the signal to our DAC. And one last thing we need to do before we be able to hear some audio at the output is to send some dummy bytes through I2S just to provide the I2S necessary clocks. So we need to call HAL I2S transmit via DMA, and we're going to transmit just some dummy bytes. We're going to keep transmitting those dummy bytes. So I define a variable for the dummy bytes. It's integer 16. I'll call it I2S dummy, an array of say 4. Just make sure it's an even number, because there is some right data and left side data. Alright, so the first one is the I2S handle. So I need to copy the I2S handle as a first parameter to this function. And the second parameter is the variable, the dummy data variable, so I need to pass it in here. But since it expects an unsigned 16, I need just to typecast it. But I kept the signed 16 for a reason, and last is the size, so it's 4 dummy data we're going to send there. Alright, so that should be it. Now when you do this, when you compile and load it to the board, you should be able to hear some audio at the output at 1 kilohertz. And if you have a scoop, you plug your scoop, you should be able to see 1 kilohertz signal. So let me compile it, load it to the board, and we're going to have a look at the board and also oscilloscope together, and we should be able to hear 1 kilohertz tone. Alright, perfect, compile successful without any errors. Now let's load it to the board and we can have a look at the board together. Alright, perfect. As you heard, we got a 1 kilohertz beep, and you saw that on the scope. We got 1 kilohertz output signal. And that's how to use the analog mode on the audio codec. And to use I2S mode, we need to get back to CubeMX first. So let me close the project. I need to get back to CubeMX, and I need to make some changes to the pinout. And one of the changes is that I need to disable the DAC, because I no more need the analog input. I'd rather need the I2S input. So I'll disable the DAC, and I also disable all the necessary ones I enable for the DAC, like the timer. I can disable the timer now, I don't need it anymore. And I need to map the word select back to PA4. That's about the only change I need to make on CubeMX. Alright, let me just double check everything is okay. So I2S settings, I still have the DMA, I still have the correct 48 kilohertz sampling rate. Alright, that's it. So generate the source code again and back to Keil. Alright, and on Keil we'll make some changes, so I can just delete or comment out those functions, the DAC function and the timer function. I don't need them anymore. And I can also comment out the timer interrupt callback because I don't need it anymore as well. And what I need to do now is that I need to first predefine the sine wave at the beginning. So just define a sine wave, store it into an array, and then output it with the I2S via DMA. And to do that, I'll first replace the dummy variable array with a I2S data array of 100 size, let's say 100 elements, is signed 16-bit. I left it signed 16-bit because I want to store negative values of the sine wave. I don't want to shift the sine wave by 1. Alright, so that's the first step we need to do. And then we need to build the sine wave. So I'm just going to copy the code over. I did it before. So this will build the sine wave similar to what we did in the first part, but this one we are building the sine wave and storing it into an array. We're not outputting symbol by symbol. So the sine value is a different name. It's called the my sine value here. Alright, so what this code is doing is just generating a sine wave. We're still using the same sample and a sample DT technique, and storing this into an I2S data buffer. The reason why we're doing two is because we have right and left data. So this one is storing the right data at the even indices, and at the odd indices are the left headphone data. Now we just need to copy this variable and output it, and the size of the DMA is equal to the sample in multiplied by 2 because we have right and left headphone data. And now all you need to do is just to select the frequency that you want output to appear at, let's say 1.5 kilohertz, and compile the code, load it to the board, and you should be able to hear a 1.5 kilohertz output at your audio jack. Very simple. And also if you hook up your oscilloscope, you also should be able to observe a very nice and clean 1.5 kilohertz audio sine wave. So let's just wait for this to compile. I'm going to load it to the board. We're going to have a look together at the board, hear the audio, and also look at the scope. Alright, perfect, compiled without any errors. Now before we get into there, let me just warn you, do not wear your headphone because volume might be very loud. Don't make the mistake I made. So you might need to reduce the volume a little bit because the tone can be very loud. So just be careful on that side, right? Let's load the code to the board and we're going to have a look together. Oh, sorry, it didn't work. I made a little mistake here. So we forget to change the mode to I2S. So we need to change the mode to I2S mode because we currently want to use the I2S to output audio, not the analog DAC. Right, so just change this and back to the board. And now we should be able to get our 1.5 kilohertz signal. Alright, perfect. We got our I2S output working and we can clearly hear 1.5 kilohertz tune and see that on this cube as well. However, there is some little thing that we haven't changed, and that's the sampling frequency. I forgot to change this. It was set to 50 kilohertz for the previous analog mode, but with the I2S mode, it's set in CubeMX to 48 kilohertz. So we need to change it to 48 kilo. And you'll find this set in I2S in CubeMX in the parameter settings. We set the audio frequency to 48 kilohertz. And with the I2S mode, this is fully controlled by the I2S of DMA routine thing, unlike the analog one, which is controlled by a timer interrupt. Alright, now just a few notes before I end the video as well. For the volume, this one is a value between 0 and 100. However, the STM Discovery board doesn't provide enough power for the audio amplifier, so it would most probably saturate at 40. So don't exceed 40 with the settings if you want to have a nice sinusoidal. Otherwise it would be saturated and clipped sinusoid. Alright, that's it. This brings me to the end of my tutorial today. Thanks for watching, and as always, if you found this video helpful, don't forget to hit like and subscribe. Thanks, and I'll see you in the next video.